Welcome to my channel. In this video, I will explain about the design and analysis of a standard ternary inverter using carbon nanotube in Cadence Virtuoso. Standard ternary inverter is designed with P-type and N-type carbon nanotube field effect transistors. To observe the properties of these transistors, select any transistor and press Q on the keyboard. Then change the CDF parameter view to Verilog A to see the properties. The gate length is 32 nanometer, effective length is 200 nanometer, and the chiral vector is 19, 0 for this transistor. You can see all the properties using the same procedure. Press Q, change the view to Verilog A. Right now the chiral vector is 10, 0. Similarly for N-type transistor. The chiral vector changed to 13, 0. Remaining parameters are same. Once the design is done, change it to symbolic view to perform the design and analysis. Then create the test bench setup, which I have created by using the same schematic. I have provided two types of sources here. Press Q and see the library name is analoglib. The source type is PWL, piecewise linear, and the number of pair of points you can have 7 to 20, 25 also. Right now I am using for 7 to create a ternary input of having a value of 0, 1, 2. You can create your own set of inputs from this. Right now I have disabled this because I have created only up to 3 nanoseconds. This source is again from the analog library with the vSource name and provide the DC voltage of 0.9 volt, and the source type is PWL. You have different types of sources available here. Right now we are going to use the PWL and select the file, specify the path of the file where it is located. I'll show that file. This is the PWL file, and the period of that particular signal is up to 15 nanoseconds. It starts from 0, 0 to and ends up to 15 nanoseconds. Once the design is done, check and save the design. Then go to launch, click on ADE Assembler. Create a new view. The view is Mastro. Click OK. It opens the ADE Assembler. On the left, click on to add the test STI_TB. Now click to add the analysis. I want to perform a transient analysis up to 15 nanoseconds. Click on moderate or conservative, liberal, any of the choice. Apply. The analysis is loaded here. Similarly, I want to perform the DC. Save operating point. Click on component parameter. Select the component. Select the source. Click on DC. OK. I want to sweep the value V3 from 0 to maximum of 0.9 in steps, which is a linear of 0.01 step size. Click apply. OK. Two analyses are loaded. Now select the outputs. You can use here or you can go from here. To be plotted, you can select on the design. I want to plot input, output, as well as the current that is entering. Similarly, VDD. All these are loaded. Then change the view from ADE Explorer to ADE Assembler. Then click on Run Simulation. See that the simulation is completed with few warnings. You can ignore them and click on Plot All Waveforms to see the response. Change the graph properties. And let me change the width of this to medium. On the right, you have the waveforms for DC characteristics. This green color represents a maximum value of 2. That means it has 3 values: 0, followed by 1 and 2. This represents the ternary output. And this is the current that is entering and switching in between. This shows the linear input. And if you observe on the left, this shows the transient response of a standard ternary inverter, and this is the input, and this shows the output for 0, 1 and maximum value is 2, and its inversion response. To calculate the average power, you can right click on this current, instantaneous current, send it to calculator. Let me clear all this. Send it to calculator. Since there are two views in this particular waveform, So you can just delete this option, multiply the value with 0.9, which is a VDD, enclose within the brackets, and use the function average. Then click on evaluate buffer. It is 216 nanowatts. You can send it to the waveform view. Similarly, I can evaluate the delay. For that, click on VT. Before that, use the function delay, input, copy this, use the function delay, then select the VT again. This time select the Vout, copy this, click on function. Signal 1 is input, signal 2 is output, threshold voltage is 0.45, and the input is in a rising, output is in a falling. Click on OK. The calculator is loaded with this expression. You can evaluate and first send it to the ADE assembler view, and you can check the value. Now it is 7.8 picoseconds delay. You can go to the master view, go to the assembler. You have this expression. You can find the values here. Rerun this simulation. See that the delay and average power is evaluated here, and you can plot again these signals.